All right. Thanks, Christian. And thanks, everyone, for coming to my talk. So today, I'm going to talk about a new class of submodular optimization, which I'm going to refer to as sequential submodular maximization, and some of its applications in ranking and assortment of the product. So this is a joint work with Arash, Asadpour, Amin, Saberi, and Shameli. So I've designed the talk so that it's a combination of high-level ideas and technical details. So whichever tribe you belong to, hopefully the talk has something to offer for you. All right. I always make that mistake. So the main focus of the talk is on online shopping application. And during the past couple of years, especially during the pandemic years, we have seen a huge growth in this market. And while this is interesting for this industry, I think from our perspective, it is interesting because it has endowed the field with a lot of interesting algorithmic questions. And in this talk, I'm going to focus on one of them, which is about how these platforms are going to display the products to the users. So the idea is you have an online platform that has a huge amount of the data about the customers. And based on those data, they have trained machine learning models to predict the user choice behavior. And now, given those models, they're trying to optimize the display of the products in order to maximize an economically justified objective, such as revenue or, for example, user engagement. So in classic retail applications, the focus was more on displaying an assortment of the products, a subset of the products that the users are going to see, and they're going to pick one of the products from that subset. But in more modern applications, when you go to the website of the online shopping platform, you usually see a vertical list of the products simply because it has a better user interface. It's easier for the users to navigate and search for the desired product. And now the task of the platform is to rank these products in order to help with the economics of the platform. And this induces a bunch of behavioral aspects on the side of the customers, because as a customer, you might have a preference to click on top products rather than the lower products. And the platform now should take this into account. And I should say, I'm going to use online shopping as a running example in this talk. But really, what I'm doing can be applied to many other recommender systems. For example, online hospitality services and lodging reservations, online freelance marketplaces and labor platforms, and last but not least, online platforms for ticket exchanges. All right, so the high-level research goal in this talk is to come up with a data-driven algorithmic frameworks to basically set up an optimization problem for the product ranking problem, given prior knowledge about the pool of the users. So having this goal in mind, you can start asking several different questions. So in this talk, I'm going to ask and try to answer two particular questions. In particular, the first question, problem number 1, pertains to improve market share and long-term customer loyalty of the platform. In particular, I'm going to try to show how we can maximize the user engagement. So what is user engagement in this context? It is the average probability of receiving a click from a typical user in such a platform. The second problem I'm going to think about is mostly related to long-term economics and societal impacts of the platform's operation. And that's the problem I'm going to call balancing user engagement. So imagine you have a pool of users with different demographic groups that might partition the user pool, or they might even have overlaps. And now the platform's goal is to guarantee a certain minimum click probability from each demographic group. All right? So with this brief introduction, let me actually jump directly into the particular model I'm going to work on. So we have an online platform that has n products to rank. The platform picks a permutation over these n products. I'm going to denote this permutation by pi. And then you will have users that arrive with different patience level and choice functions. So a user with patience level I is only going to look at the first I products in the permutation, and is going to choose one of them. So we use lambda to denote the arrival rate of users with patience level I. And fi is going to be the click probability function of user I. So the input to this function is going to be the set that is considered by the user, and the output is the probability of receiving a click given that displayed set. So just make sure we all understand the model. So imagine you have these n different types. A particular customer with patience level I is realized. Now there is a two-stage choice process. In the first stage, the customer is going to look at the first I products, and then it's going to click with probability fi of the first I elements in the list. So in this context, we are going to focus on products that are substitute, meaning that if I want to buy a shirt, if I'm interested in shirt number 1, then my interest in shirt number 2 is going to be lower. And in particular, a product is going to cannibalize another one. So there are different ways that you can model this sort of substitution. So the one that I'm going to use is assuming that these click probability functions are going to have diminishing marginal return. So they're going to be submodular functions. So they're naturally monotone. So if I show you a larger set of products, the odds of receiving a click is going to go up. So they're monotone. And then the submodularity is essentially capturing the substitution of the products. And for experts in the audience who are familiar with revenue management literature, this kind of substitution assumption arises when you think about a bunch of choice models, for example, random utility models, the Markov chain choice models, and the coverage choice models, which are quite prevalent in this literature. All right, so with these semantics, let me try to formalize the 2 questions I promised earlier. Problem number 1, maximizing user engagement. Let's drop all the bells and whistles. So I give you n monotone submodular functions, f1 through fn, with non-negative coefficients lambda 1 to lambda n. And I'm asking you the following question. Can you find, let's say, a randomized permutation such that you maximize the expected summation of I from 1 to n, lambda I, fi of the first I elements as the input to the function, which is the quantity I call as the user engagement. So this is an optimization problem where the set of permutations. But if you stare at it for a second, then you realize if I set all the lambda i's except 1 to be 0, then the very canonical problem of maximizing a submodular set function subject to cardinality will be a special case of this optimization problem. Therefore, you cannot hope for getting, so this is going to be an NP-hard problem. It's going to be approximation hard, and you cannot hope for getting any better than the 1-1 approximation due to a classic fork of Feige back in 1998. And our main result for this class, which is the sequential submodular maximization, is obtaining the 1-1 approximation for this problem. All right? So this is the first main result. Then switching to the second problem, this time I'm going to give you a pool of users with different demographic groups. Each demographic group comes with a threshold, which is the minimum click probability for that demographic group. And I'm asking the following question. Can you find the randomized permutation so that the expected engagement from each group is going to be at least the threshold? And different groups, they are heterogeneous, so they have different click probability functions and different arrival rates. All right, so now assume that this problem is a feasibility problem. So assume that there is a feasible solution. So we can show that there exists a 1-1 squared approximation algorithm for this problem, meaning that I can find you a randomized permutation such that you basically are feasible up to this approximation factor. Multiply the right-hand side by this number, and you're going to satisfy that kind of feasibility. For the special case of coverage function, we obtain the 1-1 approximation, which is the best you can do for this problem, because this is actually a generalization of the previous problem. But the question of whether you can get the 1-1 for the general class of submodular functions, it is still an open problem. All right, so our work in terms of methodology fits into the literature on submodular maximization. I can probably give an entire lecture on in this literature. And maybe I can give another lecture on the application domain, which is assortment optimization product ranking. So in the interest of time, let me just give you 5 seconds to stare at this slide. And John wants to take a photo. So all right. So in the remaining part of the talk, I'm going to first show you the simple result. These are actually quite simple. It is a very basic reduction to set submodular maximization subject to matroid with a bunch of additional techniques on top of that. And then if time permits, I'm going to show you how to obtain the second result, which is quite nice. It is related to understanding the set of admissible policies distributions over prefixes of products when you have a randomized permutation, and how it is related to a network flow problem. So I hope I will have time for the second part. I won't make any promise. All right. But the first result is easy. I think I can show you almost the entire proof in 2-3 minutes. So we are going to start with this optimization problem, or a set of permutations, the sequential submodular maximization. So I'm going to show you a chain of reductions. So the first reduction is reducing this problem to a set submodular function or a different ground set subject to a perfect matching constraint. That one is actually quite natural. And then I'm going to show you a relaxation of that problem to another set submodular maximization, this time subject to a particular matroid, a laminar matroid. And the final step of my reduction is basically showing you that this last step is actually tight. Using the structure of the problem, you can show you are not going to lose anything in that relaxation. And then finally, the last problem can be solved using off-the-shelf algorithms for maximizing set submodular functions subject to matrix constraint. And putting all the pieces together, you get the final result. So let's think about the problem again. I'm going to introduce a new space of elements. So originally, you had n products. Now I'm going to give you n squared number of products, which basically you have one product for, we have one new element for each pair of product as n position. All right? So eij is going to basically product I at position j. And given this ground set, I'm going to introduce a new set function, g of s, which is defined the following way. So it's going to be lambda 1 times f1 of s1 plus lambda 2 times f2 of s2, all the way to lambda n times fn of sn, when si is the set of elements in S that are in the first I positions. So to just give you a demonstration, suppose I pick some squares in this shape, in this graph. So that's S. Now I'm going to look at Si. So it's going to be the first basically the set of all the elements that are in the first I positions. And from this, you can actually generate the function g of S. So it is a set function, but in this exploded set. And as it turns out, this function is monotone, and it is submodular. So far, it is good news. Now you start thinking how it is related to the previous problem. So if I can identify a set that maximizes g of S, and at the same time, it's a perfect matching, meaning that each product is in exactly one position, then you are done. So you have solved your problem. So then it comes to mind that, hey, so let's try to actually solve this problem. So the catch is maximizing set submodular function subject to a matching constraint is not amenable to a 1-1 reapproximation, simply because this is the intersection of two matrices. But now we can look at the relaxation of this problem when, rather than looking at the matching constraint, I'm going to look at the laminar matrix constraint. So I'm going to have a bucket for each number I from 1 to n. Bucket I is essentially the first I positions. I'm going to put a capacity I on that bucket. And I define a matroid which says you're going to pick some set in this figure such that from the first I elements, from the first I position, you are not going to pick more than I elements. OK? So the good news is you now can maximize g of S over this matroid using off-the-shelf submodular maximization algorithms, using, let's say, the Kalinesco et al. 2011 seminal paper by basically combining the continuous greedy with a matrix rounding algorithm such as pipage rounding or swap rounding. And well, so now you have an independent set of this matroid. It doesn't give you a permutation. It doesn't necessarily need to be a matching. So here is what we do at the end. So we look at this post-processing step. So think of each product I. Let qi to be the smallest position that this product has appeared. And if the product hasn't appeared in the set that was the output of the submodular algorithm, submodular maximization algorithm, let the score to be n plus 1. Now I define a permutation to be basically the ordering of the elements based on their scores in an increasing order sorted. And I claim that if you sort the elements in this way, then the value of the original sequential submodular function in this permutation is going to be at least the value of g of S, if and only if S is an independent set of the laminar matrix. So this is a technical lemma. The post-processing step, putting all the pieces together, you can obtain the final results. All right? Good. So in the interest of time, let me not tell you that much about how to obtain the second result. But I'm going to actually tell you a little bit about the key technical kind of lemma that we use in this problem, which is interesting by itself, I would say. So imagine the following question. I give you a randomized permutation over n elements. And then you look at all the prefixes of different sizes, size 1, size 2, all the way to size n. So this randomized permutation is going to induce a distribution over all prefixes of different sizes. So now you have a collection of these distributions. So the question I'm asking is the following. What kind of constraints you can impose on this collection of distributions so that they are admissible in the sense that they can be induced by a randomized permutation? So it turns out that this characterization is the key to write down the problem number 2 as a linear programming with doubly exponentially many constraints. Then we start from there. We find relaxations and do some sort of rounding to basically get a permutation at the end, which I'm not going to show you. But the funny part is this characterization is interesting in the sense that it is related to a very cute network flow problem. And in the remaining 1 or 2 minutes, I'm going to show you what that network flow problem is. So think about the Haas diagram of the subset lattice. So you have sets, 2 to the n number of basically sets in this partially ordered set. I'm going to define a network flow problem in the following sense. Attach a super source to the empty set and attach a super sink to the set of all elements. And imagine that you start with, let's say, this distribution, the collections Vi of S. So this is basically the probability that set S is selected as the prefix of size I. So given these collections, let the capacity, inflow capacity of each node would be equal to the corresponding probability. Then I claim that if you can route 1 unit of flow from the super source to super sink, then there exists a randomized permutation that can induce these basic collection of distributions. And now we can start writing the max flow min cut, the min cut conditions that gives you the doubly exponentially many linear constraint that essentially characterize the set of admissible policies. So yeah, so this was kind of like the key technical idea. Let me tell you 2 open problems, and then I'm going to conclude. So in this talk, we talk about user engagement. In literature on assortment optimization, revenue is actually more popular objective, and whether you can get any approximations for the revenue objective is actually an open question. The second problem is tightening the gap between the 1 minus 1 over E and 1 minus 1 over E squared for the second problem, which I think is an interesting technical question. So with that, I would like to conclude my talk. Thanks a lot for your attention.
All right, thank you, Rad. So we have time for 1 question.
Yes, John.
So your second result unbalanced objective function, that the hard part is that you need a single permutation controller, as in if I are allowed to pick permutation over Taylor to people, then this would go.
Absolutely. And I should say that the deterministic permutation is too good to ask because, I mean, I can easily cook up examples for which no deterministic permutation can get any bounded approximation. So we look at randomized permutations and the guarantees in expectation, and that is actually possible. But great question. Right?
OK, great. Thank you, Rad.
Thanks.